In this presentation, we will be analyzing the article Searching and Mining Trillions of Time Series Subsequences under Dynamic Time Warping. We will first go through the introduction, motivations, and assumptions for this paper, followed by an in-depth description of known state-of-the-art optimization techniques. We will then talk about the new, novel optimizations the UCR suite provides and the results based on these techniques. When mining time series data, similarity comparisons are needed as subroutines. Two common similarity methods are Euclidean distance, or ED, and dynamic time warping, or DTW. Most research on the topic has denounced DTW as inefficient, but in the paper, the authors show that DTW is actually the best measure to optimize. The authors apply their own set of optimizations called the UCR suite to speed up similarity methods that can be applied to both ED and DTW. Using DTW with the UCR suite is an exact search and proves to be much faster than any current approximate search or exact index search. Speeding up time series data mining is critical to a lot of fields in research labs and commercial enterprises. Thousands of these institutions have trillions of data points and have spent millions of dollars and many years collecting the data. To be able to mine large data sets, sometimes with lengths in the trillions, it is pertinent that similarity search within the algorithms can be efficient and accurate. Additionally, it is important to recognize that given the vast amount of time and resources organizations spend to just gather the data, it is reasonable to assume that they would be willing to wait hours to get results and gain insight. In order for the UCR optimizations to work, it is assumed that each time series subsequence must be normalized. If data isn't normalized, the error rate can more than double, as shown with the gun-no-gun classification problem. It is also assumed that when query lengths are unknown, they cannot be indexed. Techniques known to index arbitrary query lengths are void when dealing with trillions of data points. With 1 trillion objects, it would be impossible to fit even one index in main memory, since the index of time series data is usually 1/10 of the size of the actual data. Before introducing DTW and the background for the optimizations, it is important to mention that the amount of data mined in this paper is larger than anything ever considered. In fact, mining a time series with a length of 1 trillion is larger than all of the time series data considered in all papers ever published in all data mining conferences combined. This just goes to show how revolutionary this work is with the UCR suite, and that it opens up many avenues for mining time series data in all sorts of areas. In order to understand the optimizations, some notation needs to be introduced. A time series T is an ordered list in a data set. A subsequence of T will be referred to as C, as it is a candidate match to a query Q. That is, many Cs will be compared to Q using a similarity measure, ED or DTW. To compare C to Q, a matrix, like the one on the right, is constructed and a contiguous set of matrix elements is used. This set of matrix elements is called a warping path P and is shown in red. The warping path starts and ends in opposite corners of the matrix and is constrained by the Sakashiba band. This band cannot deviate more than R cells from the diagonal. The following 5 optimizations are known optimizations that are commonly used to speed up sequential search by improving the performance of calculations involved in Euclidean distance and dynamic time warping.
The first optimization discussed by the authors is the utilization of square distance. Both Euclidean distance and dynamic time warping are monotonic and concave, thus removing the square root does not change the relative rankings of the nearest neighbors. This also has the benefit of simplifying the lower bound calculation, and it can also benefit other operations that is required by the UCR suite. Note that the author mentions that this is only an internal change and you can still use the original units, and only the input is squared, and before the output is returned it is taken as a square root, so no changes are needed. A trick when working with an expensive distance measure like dynamic time warping is to utilize lower bounding to prune unpromising candidates. Lower bounding is essentially a best guess regarding the lowest possible distance measure produced by DTW. There are multiple different lower bound techniques, and the two analyzed by the paper are from Kim and Keogh. Kim's lower bound algorithm operates in big O of n, where you need to look through each individual element compared to the query and the candidate, and you find the max square distance between the first, last, minimum, and maximum pairs of points, as highlighted in the green on the right graph. If the time series data was normalized, the lower bound produced by Kim can be computed in big O of 1 by taking only the difference between the first and last pairs, as the difference between the minimum and maximum pairs are negligible. The lower bounding technique proposed by Keogh can also operate in big O of n. This algorithm essentially generates a bounding envelope U and L that surrounds the query, and the actual value of the lower bound is computed by taking the squared sum of distances of every element not falling within the bounding envelope to the nearest orthogonal edge of the bounding envelope. Essentially a Euclidean distance for all of the elements that fall outside of this envelope. As you can see in the gray lines surrounding the candidates C. Another optimization discussed in the paper is early abandoning, and this can be applied on both the Euclidean distance and the actual calculation of the lower bound. So during the computation steps, if the current sum of square differences of either the Euclidean distance or the lower bound is greater than the distance of the best candidate that you have seen so far compared to the query, then you can directly prune your current candidate and you don't need to evaluate any further. You can see an example of this of the candidate C and the query Q. As we are computing the distance, we can early abandon at this point, as the distance produced here is already greater than the distance produced by the best candidate. Another application of early abandoning can be on the exact calculation of the dynamic time warping distance. So after the lower bound is calculated and the current candidate is still a potential, what we can do is iterate through all of the data points and incrementally compute the DTW distance combined with the remaining lower bound. As you can see in the figure, if k is equal to 0, this temporary distance is equal to the fully calculated lower bound. As we incrementally calculate the DTW distance, for example, and when we reach k equals 11, we can take the partial calculation of DTW combined with the k plus 1 measure of the lower bound. And if the combination of both of these distances is greater than the distance of the best candidate, then we can automatically prune, as there is no reason to continue evaluating. Next up, I'll hand it over to Remy to explain the last known optimization.
The last known optimization is exploiting multi-cores. Although multi-cores usually yield linear speedup, the new optimization techniques introduced will improve runtime by a much larger amount. With just a single core, the resultant speedup with the UCR suite completely dominates anything done with multi-cores. However, it is super simple to implement the same techniques with multi-cores. The next 4 optimizations we introduce are specific to the UCR suite and can be used to search with both Euclidean distance and dynamic time warping. These optimizations are new and unprecedented, and as we will later show, have impressive outcomes on overall efficiency for time series data mining. In earlier research, optimization at the normalization step had never been attempted. This is strange, as normalization takes slightly longer than the Euclidean distance computation. In the UCR suite, the first optimization is on normalization. The z normalization gets computed incrementally with Euclidean distance. This allows for pruning of both normalization and distance calculations, because if early abandoning happens, there is no need to compute the other later normalizations or Euclidean distance calculations. First, in one scan, the mean and standard deviation are calculated for use in z-normalization. Then, for each data point, the z-normalization is computed, followed by the Euclidean distance or LBKO calculations. This way, if the Euclidean distance calculations yield early abandoning, the distance calculation as well as the normalization calculations are pruned. This online z-normalization technique has an issue, however. By maintaining the statistics in this manner, there is the risk of floating point error accumulating to the point of affecting results. This is an issue for two reasons. One, since the sum of squares is computed for the standard deviation, all resulting numbers are positive, making the accumulated floating point error more extreme. And two, all research so far has only dealt with millions of data points, which allow this issue to be insignificant when comparing results. Since the data here is in the billions and trillions, this error further accumulates to a point where results are affected. To account for this, a complete z-normalization is computed every 1 million subsequences. This complete normalization simply recorrects the statistics, so the accumulated error is removed and has no significant effect on results. The next novel optimization the UCR suite describes is reordering early abandoning. In incrementally computing the distance and normalization steps, it is implied that the data points with which the steps are computed is ordered from left to right. This new optimization works under the assumption that there is a better ordering of the data points other than left to right. In a universal optimal ordering of the data points, the idea is that the data points contributing to the largest portion of the sums will be computed first. With this technique, the sums used for early abandoning will increase in size the quickest, therefore reaching the best so far faster. In other words, by using an optimal ordering of the data points, less data points will have to be searched and calculated on in order to deem the candidate inadequate. The candidate can be pruned off earlier without having to do computations on as many data points. Although there are n factorial possible orderings, the UCR suite chose an ordering based on the absolute values of the z-normalized Q. The values in Q will be compared to many candidates throughout the search, and most candidates will have a Gaussian distribution since they're z-normalized, and so have a z-normalized mean of 0. Therefore, the farther the data points in the query are from the mean, or 0, the larger the data point's contribution to the distance sum, thereby allowing us to prune off earlier. To show the effect of this optimization, the new optimal ordering can be compared to the incremental ordering with the early abandoning techniques. Without reordering, the sum would exceed the best so far after 9 of the 32 calculations. With the optimal ordering, the sum exceeds the best so far after just 5 of the 32 calculations. This is almost half as many calculations as the incremental ordering, and just a fraction of the total amount of calculations. Overall, ordering the query's data points based on the absolute values of Q is easy and simple, highly accurate, and works with Euclidean distance, LBKO, and z-normalization early abandoning techniques.
One of the most important optimizations of DTW from the UCR suite is lower bounding, which allows for the pruning of unnecessary candidates. Normally, LBKO constructs the envelope around the query, denoted as LBKO-EQ, and this process only needs to be done once. However, the roles of the data in query can be reversed by effectively creating the envelope around the candidate instead, and this is denoted as LBKO-EC. This does create more time and space overhead than LBKO-EQ. However, it can be used as a just-in-time algorithm when all other lower bounds fail to prune. This essentially avoids most of the overhead while further optimizing the efficiency of finding the lower bound to further decrease search times. As we've seen, lower bounding is necessary for speeding up time series similarity search. However, a challenge of this is finding a good balance between the tightness of the lower bound and the computational speed of finding the lower bound. After testing every currently published method for finding the lower bound, the most intuitive solution found is to use every lower bound method, which sits on the dashed line of this graph. We use each of these methods in cascading order from lowest complexity to highest until one of them is able to prune candidates. Doing this allows us to optimize the tightness of the lower bound and the complexity of finding it, and as a result speeds up search times.
The authors ran many different experiments and utilized 4 different methods to compare the results. The naive approach is normalizing the data and computing the full Euclidean distance or DTW measure. The state-of-the-art applies the same normalization techniques, but also introduces early abandoning and lower bounding. The UCR suite proposed by the authors utilizes all of the optimizations introduced earlier in the paper. And lastly, God's algorithm goal is an oracle algorithm that maintains mean and standard deviation using online O(1) incremental calculations. You can also think of this as essentially pre-computing everything, storing all of those numbers, and then evaluating later on in an online fashion that allows you to achieve O(1). Authors also claim that their implementations are very efficient, for example, utilizing a iterative implementation instead of recursive would speed up the algorithms for naive, state-of-the-art, and goal, which if you utilize a less efficient and optimized implementation, you could conclude that UCR produces better results. So the author also includes a lot of their claims and code and the actual data that they used on their website. The authors first introduced baseline tests using random walk. Random walk is essentially a way to take a random number generator and generate time series data where the future steps cannot be predicted based off of past history because the future is randomly generated. This experiment can be easily replicated by taking the same random number generator that the authors used and taking the set seed to generate a long chain of data. As you can see in Table 2, the UCR suite outperforms the state-of-the-art in both dynamic time warping and Euclidean distance by saving on runtime and being more efficient. This can also be seen with a longer query length greater than 128. As you increase, UCR still is much faster compared to naive state-of-the-art implementations. The authors also highlight 2 different ratios. The ratio of the naive, state-of-the-art, and the UCR runtime as compared to goal. As you can see, as we apply more optimizations, UCR is able to achieve a asymptotically similar runtime to goal. When utilizing UCR, as you compute the dynamic time warping distance or the Euclidean distance, utilizing this more complex distance measure only requires 1.18 times more computation, thus refuting previous claims that DTW is inefficient and slow. The paper also discusses queries of longer length. The task is to search a 0.3 trillion EEG dataset for a epileptic spike Q of length 7,000. And this data took multiple different sessions over the course of 7 days to collect, costing around $34,000. As you can see in the graph, the query Q is highlighted, and this data is a potential match to the query. Table 3 shows the time it takes to search through 0.3 trillion data points to find the best match for the query. And as noted by the author, they only utilized Euclidean distance here because dynamic time warping distance may produce false positives caused by eye blinks. As you can see, the UCR suite took a total of 3.4 hours, and the state-of-the-art took over 400 hours, thus showing how UCR is much more efficient than the state-of-the-art. Next up, I'll hand it over to Mark to discuss the rest of the experiments that the authors ran.
Most previous work in this field is focused on shorter queries that are less than 1024 data points long. Using an experiment done on DNA subsequences which have been converted to a time series, the scalability of DTW to long queries can be demonstrated. Human chromosome H2 with 72,500 data points was compared with DNA sequences from primates. Clustering was done using single linkage, and the resulting clustering gave the correct dendrogram of primates. Searching the chimp genome resulted in single-core nearest neighbor having a runtime of 38.7 days, state-of-the-art with 34.6 days, and the UCR suite only took 14.6 hours, showing that UCR DTW is capable of scaling to very long queries. However, there are still more optimizations that can be made. For searching the following query of length 64, goal resulted in a time of 9.18 seconds, and UCR took slightly longer at 10.64 seconds. If we were to pad the query along with the entire database to look like this, denoted as QP, then naive DTW will take 9 times longer, goal will take 3 times longer, and while UCR does not take 9 times longer, it does in fact have an overhead greater than 3 times more. This overhead can be avoided though if we can downsample the data, conduct the search on this data, and then upscale the results to the original data. So revisiting the chimp genome experiment we discussed, by downsampling the data to a ratio of 1 to 10, the search time was decreased to only 475 seconds. Then we are able to set the best so far to the value of RD times 10, where RD is the best matching subsequence distance. As a result of this, searching over the upscaled data reduces the search time from 14.64 hours to only 4.17 hours. By running the search over downsampled data and upscaling the result, we can significantly speed up search times, which can prove to be useful in many real-world scenarios where data is oversampled. Recently, low-powered sensors for real-time monitoring have become increasingly popular. One of the criticisms of DTW is that it is not possible to be done on these low-powered devices due to the complexity of the algorithm. So some common workarounds for this are to use shorter test and class templates, using low cardinality DTW with integers, or using DTW approximations on piecewise linear approximations of the signals. After testing the UCR suite on data coming from an ECG running at 256 Hz, it was found that the UCR suite is magnitudes faster than the current state-of-the-art methods. While these tests were done using a multi-core desktop, the results are about 29,000 times faster, indicating that it is possible to be run on low-powered devices. A major implication of the UCR suite is its applicability to many other data mining algorithms, needing only simple updates to the code. One example presented is time series shapelets, which when tested reduced the runtime on the face dataset from 18.9 minutes to 12.5 minutes. Online time series motifs also had a significant speedup when tested on the original EEG dataset, going from 436 seconds to only 156 seconds. UCR was also applied to some classifying and clustering algorithms. Classifying musical scores and ancient coins had a speedup factor of 11.8 and 16 respectively, and clustering starlight curves had a reduced runtime of only 1.47 days compared to 16.57 days originally. These results show just how versatile the UCR suite is, while only requiring simple copy and paste updates to the code. The evidence from the article has demonstrated the UCR suite as a groundbreaking technique to improve the speed and applicability of dynamic time warping. UCR DTW has many advantages over embedding-based DTW, including giving exact results instead of approximations, 0 parameters are needed, 0 pre-processing is needed. EBSM is also incapable of Z-normalization, which is necessary for algorithm stability. There's no limit on query length, and lastly, it can handle exact queries under uniform scaling. So the bottom line is that UCR DTW is simply faster than the current state-of-the-art methods by combining many existing techniques with DTW. These findings show that the enhancements provided by the UCR suite have the potential to make major advancements in data mining across many industries.